In my opinion, the core idea of the no-arbitrage pricing theory is something that even high school students could understand if it's explained properly. So let me start with a non-finance example of fruits baskets of apples and bananas. The main assumption, and probably the only important assumption for the basic no-arbitrage pricing theory, is that anyone can freely buy and sell products or assets without any fees. In particular, you can buy and sell for the same price. In reality, of course, after buying a watch for £100, you cannot possibly sell it immediately for the same price, £100. Usually it's less. But for the basic no-arbitrage pricing theory, a purely frictionless economy is assumed so that everyone can buy and sell for the same price. Okay? That's pretty much the only assumption we need for today's theory. Okay, now given that assumption, I want to ask you, if one apple is priced 50 pence, then what is the price of a bundle of 3 apples? A bundle of 3 apples should be priced 150. Why? Well, suppose it is 151. What would happen? You can buy lots of apples. You can buy 3 apples. Each costs 50 pence. And then you can bundle them, making a bundle of 3 apples. The bundle costs 151, so you can sell the bundle for 151. After doing this transaction, 1 pence is left in your hand. You might think 1 pence is nothing, but what about buying 3 billion apples? Each apple costs 50 pence. Then you make 1 billion bundles, and each bundle can be sold for £1.51. After those transactions, 1 billion pence is left in your hand. That's free money, arbitrage opportunity. A similar thing happened when the price of a bundle of 3 apples is 149. In that case, you can buy lots of bundles, each costs 149, and then you break the bundles and sell these apples separately. And each apple can be sold for 50 pence. Again, after doing this transaction many times, billion times, free money is left in your hand. Again, this is arbitrage opportunity. Okay? If there is any such arbitrage opportunity, then everybody would want to do so. So, if one apple is 50 pence, then the non-arbitrage pricing theory says that a bundle of 3 apples should cost exactly 3 times 50 pence. That is £1.50. Now let's consider a little bit more complicated application of the no-arbitrage pricing theory. Supposing that 3 bundles of fruits, 3 baskets of fruits are currently available in the market. And these are the 3 bundles available. Bundle A contains 2 apples and 1 banana, and it costs £1.30. Bundle B contains 5 apples and 2 bananas and costs £3. Bundle C contains 3 apples and 3 bananas and 1 pineapple, and it costs £4.70. Again, you can freely buy and sell these bundles of fruits, but these 3 bundles are the only bundles available in the market. In particular, even if you want to eat just 1 apple, you can't simply buy just 1 apple. You have to buy either bundle A or bundle B or bundle C. That's the setting. Question 1. What is the implied prices of an apple and of a banana? Now this is a high school problem. How can we solve it? Let the price of 1 apple be PA, and let the price of 1 banana be PB. Then the prices of these bundles, bundle A and bundle B, imply the following equations. 2 times the price of 1 apple plus the price of 1 banana should be equal to £1.30. That's what bundle A implies. Now the price of bundle B implies that 5 times the price of 1 apple plus 2 times the price of 1 banana should be equal to £3. If you solve this system of equations, you get the price of 1 apple and the price of 1 banana. Of course, you can express this system of equations by using a matrix. Once you have this matrix notation, then if you use some inverse function of Microsoft Excel or any other computation software, you can easily get that PA being equal to 40 pence and PB being equal to 50 pence. You don't have to use matrix formula, by the way. You can simply solve this system of equations. Question 2. If you want to buy just one apple and no bananas, what should you do? How much would it cost to do so? Again, in this world, no one sells just one apple. But there is still some way to get exactly one apple. That is, if you buy some bundles and at the same time sell other bundles, you can successfully end up with just one apple left in your hand. Let's see. Let YA and YB be the number of bundles A and B you should buy or sell. If you buy YA units of bundle A and YB units of bundle B, then how many apples and bananas will you end up with? Well, the total number of apples you will have is 2 times YA plus 5 times YB, because bundle A contains 2 apples and you buy YA units of bundle A, and bundle B contains 5 apples and you buy YB units of bundle B. So 2YA plus 5YB is the total number of apples. Same for bananas. Bundle A contains 1 banana. Bundle B contains 2 bananas. So if you buy YA units of bundle A and YB units of bundle B, then the total number of bananas is 1 times YA plus 2 times YB. You just want one apple. You don't want any bananas. So you want the number of apples you end up with to be equal to 1, and you want the number of bananas you end up with to be equal to 0. Okay? Again, we have a system of equations. If we solve it, YA is equal to minus 2 and YB is equal to 1. That is, if you buy bundle B, 5 apples and 2 bananas, and at the same time sell 2 units of bundle A, then you end up with 1 apple and no banana. The cost to do so is minus 2 times £1.30 because you sell 2 bundle A's, plus 1 times £3 because you buy bundle B. This is equal to 40 pence. And it is not coincidence that this cost is exactly equal to the theoretical price of 1 apple we found in the previous question. Question 3 is pretty much the same. If you want to buy just 1 banana and no apples, what should you do? Well, again, let YA and Y be the number of bundles A and B you should buy or sell. Then the total number of apples you have is 2 times YA plus 5 times YB. You don't want any apple, so this should be equal to 0. The total number of bananas you have is 1 times YA plus 2 times YB. And you want exactly 1 banana, so this should be equal to 1. You have a system of equations, you solve it, YA is equal to 5 and YB is equal to minus 2. That is, if you buy 5 units of bundle A, well, that would be 10 apples and 5 bananas, and at the same time sell 2 units of bundle B, so you are selling 10 apples and 4 bananas, you will end up with just 1 banana. And the cost to do so is 5 times £1.30 minus 2 times £3. So that's equal to 50 pence. This cost again is equal to the theoretical price of 1 banana we found in question 1. And this is not coincidence. Question 4. What should be the price of bundle D, which contains 2 apples and 2 bananas? Imagine there is such bundle newly available. There are 2 approaches to this question. In question 1, we already found the theoretical prices of apple and banana are 40 pence and 50 pence respectively. So, if bundle D contains 2 apples and 2 bananas, then the theoretical price of such a bundle should be 2 times 40 pence plus 2 times 50 pence equal £1 80 pence. There's another approach to this question. So imagine you replicate this bundle D by buying and selling bundles A and B. Again, you buy YA units of bundle A and buy YB units of bundle B's. You want exactly 2 apples and exactly 2 bananas. You solve it. YA is equal to 6, YB is equal to minus 2. That is, if you buy 6 units of bundle A's and at the same time sell 2 units of bundle B's, you end up with 2 apples and 2 bananas. How much is the cost to do this replication? That is 6 times the price of bundle A minus 2 times of the price of bundle B equal £1 80 pence. And both approaches imply that the theoretical price of this new bundle should be exactly £1 80 pence. Question 5. If the market price of bundle D is different from the price we found in the previous question, what would happen? The answer is there would be an arbitrage opportunity, and everyone would try to take the arbitrage. So in the previous question, we found that 6 units of bundle A and minus 2 units of bundle B together can replicate bundle D, 2 apples and 2 bananas, and that replica costs £1 80 pence. But bundle D and replica are exactly the same thing, 2 apples and 2 bananas. If the price of bundle D is different from the price of the replica, 180, then everyone can buy the cheaper one and at the same time sell the more expensive one to get free money. So the bundle D's price should be exactly £1 80 pence, and the argument I've just made is summarized here. Okay? So far we've had just 2 fruits and 2 bundles, apple and banana, and bundles A and B. But the same sort of argument can hold even if we have 3 fruits and 3 bundles. Imagine we have bundles A, B, and C, and bundle C costs £4 70 pence. What should the price of a pineapple be? This question is very similar to the first question. Just denote the price of apple, the price of banana, and the price of one pineapple by PA, PB, and PP. The prices of these bundles imply this system of equations. You solve it using an Excel, and you can find that the price of one pineapple implied by the prices of these bundles is exactly £2. In other words, even if one pineapple is not directly sold in the market, by trading bundles A, B, and C, you can replicate one pineapple, just one pineapple, and the cost to do so is £2. I want to conclude today's class by introducing some terminology. A redundant bundle is a bundle that can be replicated by buying and selling existing bundles. In our fruits basket example, we had bundles A and B, and then bundle D can be replicated by using bundles A and B. And in that sense, bundle D was a redundant bundle. Okay? Then the no-arbitrage pricing theory is just summarized by the following 3 lines. The price of any redundant bundle should be implied by the prices of existing bundles. It should be equal to the cost of replicating that bundle. Otherwise, there is opportunity of arbitrage. Okay? And actually, the no-arbitrage condition is necessary for any notion of competitive equilibrium, which basically sets demand and equal supply. Because if there is any arbitrage opportunity, then all the investors try to take the arbitrage, buying the cheaper one and selling the more expensive one. So demand can never be equal to supply. So the no-arbitrage condition is actually a very weak condition. Finally, our story about bundles of apples and bananas and pineapples goes through even if there are 10 different kinds of fruits and 10 non-redundant bundles of fruits. It's a game about solving system of equations. When you solve a system of equations with 10 variables and 10 equations, probably you won't express that system of equations using a matrix so that you can solve it using an inverse function of Excel, but the theory behind it is the same.